Welcome to my talk on approximating multistage matchings. Non-perfectness is not an option. My name is Niklas Troost, and what I'm going to present you now is joint work with Markus Cimani and Tilo Videa. So let's jump right in with the obvious question: what is a multistage perfect matching? First, let's remember the classical perfect matching problem. In this example, we are given a bipartite graph that shows which pirates are compatible to which parrots. And as we all know, every pirate likes to have a parrot at their side. So the task is now to find a unique compatible parrot for each one of the pirates. And here we can just pair them up row-wise like this. In more general terms, a perfect matching is simply a set of edges such that no two of these edges share an endpoint, and each vertex in the graph is incident with one of the edges. But what if the compatibilities between the pirates and the parrots change over time? So, for each year, we may consider the same pirates and the same parrots. And if we have a match in 1 year, it makes sense that we keep it, if we can, in the next year. So what we want to do is we want to maximize the sum of common edges in consecutive years. However, keep in mind that we still want to find a perfect matching in each year. So in each year, every pirate and parrot must be matched with someone. In year 2, in our example, we do not have to think too hard how we can do that and can simply choose the exact same matching as in year 1. And the number of common edges between these two stages is now 3. Looking at year 3, it's not so easy. We cannot keep any of these edges and we must settle for another solution like this. But now we can see that maybe we didn't choose right in the first 2 stages and we can do better for an overall better profit. In year 2, we can switch our perfect matching to be the same as in year 3. And now in year 1, we can adjust our matching like this so that we get an overall profit of 4. So how can we formalize this? We do this by using the concept of multistage graphs. We're given a single set of vertices and an ordered set of edges over these vertices. And here in this example, we've got 2 sets, the red ones and the blue ones. And we now want to look at single stages in this multistage graph, that is, the graphs induced by one of the edge sets. So induced isolated vertices are ignored. And we refer to the stages as G1, G2, and so on. And another way to think about this is if you just imagine a multistage graph is a sequence of graphs over the same edge set. So in this multistage graph, we now want to define multistage perfect matchings as we've already used them before. So a multistage perfect matching is now just a sequence of perfect matchings over the respective stages. So Mi is a perfect matching for Gi. And to measure the similarity that we aim for, we use the profit, which is just the sum of intersection sizes between consecutive matchings. And the problem of finding a multistage perfect matching such that the profit is maximized is called MIM, which is short for multistage intersection perfect matching. And we are not the first to consider this problem. It was shown to be NP hard for at least 6 stages by Gupta and others. They also introduced the problem. And it was later refined by Bumpis and others. And they showed that the problem is already NP hard on 2-stage graphs. In fact, we show in our paper that it is already enough to consider two-stage graphs where each stage is only consisting of disjoint cycles of even length. And Bumpus also looked at a closely related problem, finding a maximum, not necessarily perfect multistage matching, which is APX hard. They also provided a 1/2 approximation for this problem, and the objective is to maximize the sum of the profit function and the weights of the individual matchings. And we will see in a minute how this relates to our problem. So, and as you may have thought, multistage problems are not restricted to matching problems. There is a large variety of multistage problems that are generalizations of classical problems. I've listed some of them here, but let's have another look at the maximum multistage matching problem by Bumpus. So if we have uniform edge weights, perfect matching maximizes the weight of a matching. So if we have a perfect matching in each stage, we would automatically get the largest possible value for the right part of this sum, which leaves us with just the problem of optimizing the profit. In our example, the objective value for the maximum multistage matching problem, as defined by Bumpus, is 13. We've got a profit of 4 plus 3 times a matching size of 3. However, the maximum multistage matching problem does not strictly require perfect matchings. So if we adjust the matching in year 1 like this, we decrease the size of this matching by 1, but at the same time also increase the profit by 1. So this is an optimal solution for the problem by Bumpus, but it is not feasible for our problem, where we want to have a perfect matching in each stage. So regarding optimal solution, this effect could be circumvented if we scale the weights of the edges appropriately. But the approximation algorithm by Bumpus might still return non-perfect matchings to achieve its approximation guarantee. So in our paper, we came up with a way to approximate the multistage perfect matching problem while obeying this hard constraint of perfectness. And for this, we make use of a simple technique to solve a little auxiliary problem, finding an edge-preferring perfect matching. Given a single-stage graph and some edge set f, the task is now to compute a perfect matching that contains as many edges of f as possible. And this is easily achieved by the following algorithm, which we call pref_pm. We set all edges to uniform weight 1, and edges in f are made a little bit heavier. If we now compute a maximum weight matching, we automatically get a perfect matching where the number of edges in f is maximized. Our approximation algorithm for the multistage matching problem is split into 2 parts. First, we will only consider two-stage graphs. Then we will show how we can use this to get an approximation for arbitrarily many stages. So we are given a two-stage graph consisting of the red set of edges E1 and the blue set of edges E2, and we call their intersection E cap. Our algorithm 2IM approx is now using a prefer and ignore technique, preferring some edges while ignoring those that we've already preferred once. And we start with the candidate solution M1, M2, and a set S, which is all of them are initially empty. The candidate solution will be updated throughout the algorithm and is what is returned at the end. The set S will later contain the edges that we've already seen. Okay. First, we use our pref_pm algorithm to compute a perfect matching M1 bar on the first stage, such that it contains as many edges of the intersection E cap as possible. In the second stage, we now compute a perfect matching M2 bar, which is the best fit for M1 bar, meaning it contains as many edges of M1 bar as possible. And if the profit of this pair M1 bar, M2 bar is higher than the profit of our candidate solution M1, M2, we will update the candidate solution and go on. And after all, we mark the edges of M1 bar as seen, and then we repeat the procedure until each edge in E cap has been marked as seen. The next matching M1 bar in the next iteration now prefers edges in E cap, but ignores those that we've already seen, and M2 bar is the best fit for this new M1 bar candidate. Okay, this is the algorithm. Let me now give you an intuition why this cannot be too far off from an optimal solution. In fact, we are always within a factor of 1 over square root 2 times the size of E cap of the optimal solution profit. So for the proof sketch, consider an optimal multistage solution M1 star, M2 star, and assume that their profit is not 0. Otherwise, any pair of perfect matchings would be optimal since there is nothing to optimize. If the optimal profit is small, that is, if M star cap contains at most square root 2 times E cap many edges, then any solution with profit at least 1 suffices to meet the approximation guarantee. And this is easily achieved by our algorithm, since the auxiliary algorithm, prefpm, will always find the best fit for any perfect matching M1 bar. If, on the other hand, the optimal intersection is large, we cannot miss it during our algorithm. That is, since some large part of E cap is actually realizable in a perfect matching, our prefpm algorithm must hit this large part eventually. Suppose this wasn't the case, and in each iteration only few of the unseen edges of M cap star are hit by M1 bar. But since we do not stop until each edge in E cap has been seen, we necessarily need a lot of iterations. And at the same time, the unseen edges of M cap star are not hit. So they take up a relatively large part of E cap. This now has the effect that M1 bar prefers those edges. No, they are guaranteed to be matchable at the same time, but they also take up a large part of those edges that we want to prefer. Yes. Thus, we can show, and this requires some algebra that I'm going to spare you now, we must eventually hit a large part of these unseen edges, which is a contradiction. So, since the prefpm algorithm is now finding a best fit M2 bar, this will now realize the largest possible profit with respect to this M1 bar. And this actually suffices to meet the approximation guarantee if the optimal profit is large with respect to E cap. And the detailed proofs are, of course, in our paper. Okay, this was the two-stage approximation algorithm. How can we use this to get a multi-stage perfect matching for arbitrarily many stages? So let's assume we have an alpha approximation algorithm A, just like the one we've seen, for the two-stage problem. And we can now use this algorithm A as a black box to compute an approximation for each consecutive pair of stages. You can see here we have used an auxiliary graph, which is just a path, P. And each vertex here represents a stage, and the objective values of the approximate solutions of neighboring stages is denoted with Wi. And now we compute a maximum weight matching on this path, and we call it MP. So for each vertex in P, for each of the stages, at most one edge is in this matching MP. And this allows us now to iterate over the edges of P. If an edge I is in MP, we set the matchings for Gi and Gi plus 1 to the respective approximate solution that A, and the algorithm, black box algorithm A, has output for us. And since MP is not necessarily a perfect matching, some stages may not be provided with a solution this way, and for these we just choose an arbitrary perfect matching and do not care about the intersection profit. So what can we say now about the approximation guarantee of this algorithm? First of all, our black box algorithm A is an alpha approximation for the two-stage problem. That is, we get an upper bound for the optimal value of each two-stage problem, and this also directly is an upper bound, gives us an upper bound for the optimal value of the multistage problem. And as this cannot be larger than the sum of the upper bounds for all its two-stage problems. Second, the weight of the matching MP is at most half the weight of all edges of the path P. And third, the profit of our algorithm's output is at least the weight of MP. Maybe it's a little larger because we do not specify how we choose the arbitrary perfect matchings. So in combination, this proves that this algorithm is an alpha over 2 approximation. And I don't know about you, but I was quite surprised that this generalization from 2 stages to arbitrarily many stages only reduces our approximation guarantee by a factor of 1 over 2. I was thinking it would be dependent on the number of stages. So, what did we do? We improved the existing hardness result even further and showed that the problem MIM is even NP hard for 2 stages that only consist of disjoint cycles of even length. We provided an approximation algorithm 2IM-approx for the 2-stage restriction of the MIM problem, and the approximation guarantee is 1 over square root 2 times size of E cap. And using 2IM-approx as a black box, we now get an approximation algorithm for the unrestricted MIM problem as well. And the approximation guarantee here is 1 over square root 8 times the maximal intersection size of 2 consecutive stages. Additional results in our paper, which I did not explain in this talk, are that we can reduce a MIM stage to a 2IM stage, to a 2IM MIM instance. We can reduce a MIM instance to a 2IM instance, which has the same profit. This is not necessarily better than our previous approximation result, but this implies a nice theoretical result, because if we can show that MIM is APX hard, then we know that the 2-stage problem must be APX hard as well. And we further looked into a variant called MUM, the multistage union perfect matching problem. And here the objective is to minimize the union of consecutive solutions instead of the intersections. And we provide multiple approximation algorithms for this problem as well. So open questions are, of course, is there any better approximation for the two-stage intersection perfect matching problem? Or if the problem may be APX hard? And maybe there are better approximations if we consider a larger number of stages at once, maybe 3, maybe 4. And we know that this would automatically yield a better approximation for MIM as well by a small modification of our MIM-approx algorithm. And finally, we ask ourselves if our techniques could be generalized and used for other, not necessarily matching multistage problems. And by now we can answer this problem, this question in the positive, and we're currently working on a follow-up paper on this exact topic. So I hope you enjoyed my presentation and thank you for your attention.